And let's move forward, okay? Now, MOSFET review again. This is for your exam, right? I'm doing the review. So you see, but I'm not just using the old stuff, right? I use new stuff. Again, I want you to have this immersion, right? We come back again to what we have learned before. This is the MOSFET structure, a 3D one. This is the gate, this is source, this is drain. Then our electrons move in this way, right? This picture is very nice. I think it's from C. Now we draw the band diagram of this structure. This is the conduction band, and this is the intrinsic level, and this is the valence band. Now, do you see that basically when you apply a VG larger than 0, what you do is you pull this band down, right? So that you can get more electron. Electron can go through. They cannot go through the body. Okay. Actually, I should go this one. This one is the flat band condition, right? This is VG equal to VFB. So it is flat. Right? Anyone don't see that this is a flat band condition, please let me know. Right? Can you reorientate yourself so you understand this? We always draw a 2D diagram. Now this is a 3D one. Electron you just like water. You want to go from here to here. You need to go over this barrier. When you apply a gate bias, it makes the barrier at the surface low. So you go through the surface. And then if you add drain bias, then you will see this one. Usually we only draw a 2D version. But now you see the 3D version of a transistor. So, make sense or no? Any question? I hope that you understand everything on this figure. Then let's go to subthreshold slope. This is, I think, is also in the assignment, right? Now, I want to review subthreshold slope with you one more time. What is subthreshold slope? This is VG. This is ID. But in the log scale. I know that actually some of you can annotate. Does anyone want to annotate my graph? Draw the ID VG curve? No one? How should I draw it? Can someone tell me? Is this the graph? Or this is the graph? A or B?
It's A since it's log scale.
A.
I think it's A.
Very good, because it's log scale, right? So subthreshold slope is telling us I have VG1, VG2, and then I have ID1 and ID2. What is the meaning of subthreshold slope again? Someone tell me.
It's the change in the current due to change in the gate voltage.
Correct. But how do I calculate? How do I report the number?
For like it's 10 or 10 times increase in current, something for the change.
Yes. Yes. 10 times change of current. So how much voltage you need to change in order to change 10 times of the current, right? Now, but again, we say that it's not that simple. You're right. We try to change the gate from VG1 to VG2. But the current actually is controlled by the surface potential, right? Like this one. This is VG1. And then it becomes VG2, right? But this potential is actually phi1 becomes phi2. Usually VG1 Vg1 minus Vg2 is not equal to phi1 minus phi2. Usually phi1 minus phi2 is smaller. Okay. And this is because we have a depletion capacitance. C ox, C depletion, and this is phi. Okay. So this corresponding to phi1, this corresponding to phi2, right? For subthreshold slope, you are right. We want to see, right, how much Vg needs to change for 1 decade increase in current or just in ID. Okay, and we know that already. We know that it is delta phi s divided by delta I, right? Just the surface potential is kT over Q, not 10. We know that this is the equation, right? If you change the surface potential by that amount, then I'm going to be able to change the current by 10 times. This is the equation. But however, between the Vg and also the phi s, they have some relationship. What is that? We know that delta phi s is just equal to C ox divided by C ox plus CD times Vg. Just use the capacitor divider effect, right? So you change the Vg by 1 volt, it doesn't mean that your surface potential changed by 1 volt. Okay, so you combine this together, you see that what you care about is subthreshold slope is more like delta Vg delta I is just equal to delta Vg delta phi times delta phi delta I. It basically tells you that the control of the current by Vg go through the middleman phi s. This middleman always takes some commission, okay? And this commission is equal to 1 plus CD divided by C ox. And then you have KT over Q log 10. And we call this N, or 1 plus alpha. Some of you might get lost in the math, but don't worry. The main point is this. You have the equation already, but you want to know why you have this equation. The main reason is that you know that you have long ideality factor. I try to change the surface potential through Vg, but they are not all go to the phi s because of this potential divider effect. Maybe I change Vg by 1 volt, the surface potential only changed by 0.8 volt. So my current does not increase as much as I want. So originally my subthreshold slope may be 60 millivolt per decade, but I need to increase more to 80 millivolt per decade in order to have my current increase by 10 times. Right, so this is another view, right, of subthreshold slope. Any questions? Or anything that is confusing, right? Please do help to ask question. Is helping your classmate. So if I ask you to find the subthreshold slope of of a transistor. I hope that you can do that. Okay. Okay, finally, let's go to another topic, ballistic transport. We have been talking about the MOSFET equation, right? How do we derive the MOSFET equation? We always say velocity equal to mobility times E. This is non-ballistic. What does it mean? It means I accelerate the electron for a while, then it hit something, lose the energy. And then accelerate again, hit the and can lose energy again. Overall, it's going to transport in a FH velocity related to the electric field by mobility. And that's called mobility. That makes sense, right? It's just like you run into a hall, someone push you, you hit someone, you slow down, and someone push you again. Let's say the invisible hand, which is the electric field, and then you slow down again. Eventually, you go through the hall, the room, within certain time. So you have a FH velocity, and so your velocity equal to mobility times electric field. Well, if you are smaller guy, you may go through easier. Actually, depends. Maybe you're too small. They just keep back scattering you. You actually have smaller mobility, right? Under the same electric field. Well, what if my transistor is so short, I don't hit into anything before I emit from the channel to the drain? It's just like you go into a hall, only 1 or 2 person there in the room, only 1 or 2 person. You have no chance to hit anyone. Then I cannot use mobility because I keep accelerating. This is electric field. Think about you run over the cliff and you're not hitting the air. No gravitational force. You have gravitational force. No air friction. You will just keep going, right? And that is called ballistic transport. So if that is the case, the currents really just depends on the concentration of electron at this injection point. We call it injection point. And then the effect, and then the velocity at this point. Because this is the limiting factor, right? I have a Qn electron here, and then it is travel at velocity V effective. Then the current, of course, is Qn times E effective. That's it. I don't care what happened afterwards because it's ballistic, right? You just keep going. The dominating part is this injection point. And that is how you calculate the current when you have ballistic mobility, right? But what is the velocity? What is the velocity? Can you tell me what is the velocity at this point? Anyone have any idea why the electron has velocity at that point? Why the electron? Oh, let's don't talk about electron. What if it is a gas? Why the gas has velocity at that point?
Thermal motion?
Thermal motion. And same for electron. It is just the thermal velocity. Okay? So you have, if you remember, 2/2 3 kT is the thermal energy. And it's almost equal to half mv squared, which is the velocity, right? What is thermal energy? If you look at atom, nothing is thermal. It's again mechanics. Thermal is a result of statistics, right? You look at one atom, one gas molecule, one electron molecule. This is electron gas, a lot of electron. They vibrating, right? And they have a certain velocity. So that's why all the electrons are traveling at that velocity when they emit to here. Later, they got electric field to drift them further away. But thermal velocity is so large, they're the dominating part. So that is the velocity at injection. Okay? So we call it thermal velocity. But however, in reality, the effective velocity is larger than the thermal velocity because of some quantum effect. We won't go into detail, but it's better than the thermal velocity. Okay, and you don't need to know what. All you need to know is that, hey, electron come in very slow, and then it becomes very fast because of the electric field. But we don't care because this is non-ballistic. I don't care how fast you are. It's just like flushing the toilet. When you flush the toilet, those go away. Those water went away very fast, right? But it's limited by the source of the water. And that's what we are doing. We find what is the density of the water and how fast they come into my toilet bowl. And then for the rest, they go very fast. The total current still limited by this. That's why we just do this ID set equal to Q times EF. Okay. Finally, just to show you this, you don't have to even put in the cheat sheet. But I want you to know that our transistor is so short now, especially for free fine material, right? They have very long scattering length. Some can go to micron. And if you go to the cryogenic temperature, is even longer. So there are lots of ballistic transport. It means no scattering. Okay. So compare with what we learned before. This is long channel. This is short channel. Short channels is not even good enough. This is ballistic transport. Short channel, you still have scattering, okay? So that's all I have for today. Thank you. Let me know if you have any questions.
Hello?
Yeah.
Professor, as you said, like there's no due date for assignment 3, right? Even like there will be no point deduction.
No, there is no late submission. It means if you are late, you get 0. I did not say it's no due date. No late submission option. So you need to submit before Sunday.
Okay, Professor.
Okay.
Okay. Thank you, Professor.
Okay, thank you.